In this lecture, we are going to talk about the inverse Laplace transformation of any function. So if we are having a function in the frequency domain and we want to convert it into a time-bound domain by taking its inverse Laplace transformation, and finally we would be having our final answer in the time domain. So there are two major methods that we can use to find the inverse Laplace transformation of any function. The first one is by using the definition of Laplace inverse. But we will not be using this technique as it includes this complex integration, which is not very pretty to do. So we would be using another technique which is quite simple, and we would use the table 2.1 and 2.2 for that. The links are in the description, or they might be shown right here in the top right corner. So the second technique is that we know that Laplace transform of any function provide us with the function in the frequency domain. Now we want to find the inverse Laplace of this function to find our initial function, right? So if we have a table which is 2.1 in this case, so we are having a table which gives us the Laplace transformation of all the important cases that we can have for any system. And if we have the Laplace transformation of those, then we can convert the function we are having in the frequency domain in that form, and then we would be obviously looking at our final answer for the inverse Laplace. So that means that our Laplace inverse of that function would be equal to our function in the time domain, right? So we would be looking at that table that is available according to that function that we are trying to find inverse of, and we will be more clear when we move to the example, and we will be discussing all the related cases regarding the inverse Laplace. So we will be using this second technique, which is quite easy to approach. Let's go through that. Let's start with the most simple example, that is f of s is equal to 1 by s. Now if you are asked to find the inverse Laplace of this function, then right, now we will be trying to look this function right here in our table 2.1. And if we find this function in our table 2.1, we should be obviously on the once the Laplace transform is being taken, right? And if you look at the table 2.1, we would see that Laplace of a unit function is equal to 1 by s. So Laplace of a unit step function is 1 by s. That means that Laplace inverse, once you take the Laplace inverse of 1 by s, our initial function would be unit step function, right? So that's the technique we will be following in order to take the inverse Laplace of the functions that we are having in our frequency domain, so that it can be converted into our time domain. Let's move to some examples, and then from that we would be moving to all the cases that we can have, and we have to find the inverse Laplace for each case. Now, unlike previous example, here we have a function where this is not exactly available in our table 2.1, right? So we need to reduce this function into a form that is available in our table, right? And from that table we would be able to find the inverse Laplace easily, right? So for the reduction we need to factorize our denominator. Let's do that. And we have reduced it to this form, and then we can cancel out the s plus 1 with the square, and we would be left with 1 divided by s plus 1. Now initially we had this function and we reduced it to this form. Now if we check it in our table 2.1, then we would see a Laplace transform like this. So the Laplace transform of this function in the time domain gave us this fraction in the frequency domain, right? And this is exactly like what we have right here, right? Now that means if you want to find out the inverse Laplace of this function, which is actually this function, then we can relate it to this one, and our Laplace inverse would be the function right here, which in this case, if you want to find out the Laplace inverse of 1 divided by s plus 1 would be equal to exponent power negative sa, in this case is 1, so it would be negative t into unit step function, and this would be our Laplace inverse for the function we are having right here, right? So it was just a simple example, and let's move to some other examples. Now if we look at this example and we want to find the inverse Laplace transformation, so we cannot simply convert this into the form that is available in our table 2.1. If we factorize it, we would get our final form as s plus 1 divided by s minus 2 into s minus 3, right? And obviously we cannot cancel them out so that it can be converted to the form of that we were having as 1 divided by s minus a in the previous case, or s plus a in the previous case. But we can separate these denominators factors using another technique, which is the most popular one known as partial fractions. Using that technique, we can separate these factors in the denominator, and we would be getting the result as and once we have our result in this form, then we would be able to see the exact form in our table 2.1, and we can find out the Laplace inverse of each one separately. And once we have this function in this form, then we can relate it to the table 2.1, and that was our Laplace inverse of exponent power negative 80 into unit step function is equal to 1 divided by s plus a, and this function relates to each one of them, and then we can find out our Laplace inverse for each one of them, which should be this. And the first requirement for conversion of a fraction into its partial fractions is that it must be a proper fraction. If it is not a proper fraction, then you cannot convert that fraction into its partial fractions. And what do we mean by proper fraction? In a proper fraction, the degree of numerator is always less than the degree of denominator. In other words, the highest power of denominator must be more than the highest power in the numerator. Like in this case, the highest power is cube, while the numerator is having the highest power as square, so it is a proper fraction. But in this case, as you can see that the highest power in the numerator is more than that in the denominator, and this is an improper fraction, so we cannot convert this one into its partial fractions, but we can convert this one into its partial fractions because it is a proper fraction. Now what if we are having an improper fraction? So for converting it into a proper fraction, we simply use the division technique, which is dividing the numerator by the denominator, right? And dividing the numerator by denominator, we would be able to convert it into the proper fraction, so that the degree of the denominator gets higher than that of the numerator. This is the first requirement for conversion of a fraction into its partial fractions. Now the partial fractions are divided in three major cases in order to find the partial fractions for any fraction. And these divisions are based on the roots of the denominator of that fraction. Now, what do we mean by roots? So, a root is, for example, if the denominator is in the form like a square plus bs plus c, then equating it to 0, and whatever the solution of this equation is, which means that whatever possible values of s can be in order to satisfy this equation, we would call those values as the roots of this equation, right? So if the denominator is in this form, then its roots will be determining which case to follow, right? So if the roots of the denominator are real and distinct, means they are different from each other and they are also real numbers, then we would follow this case. If the roots are real and repeated, that means they are real numbers but there are one or two roots that are repeated again and again. Now if the roots are imaginary, that means if it is a complex number or imaginary number. Now in order to find the roots, we generally use the quadratic formula. If it is not factorizable or any other case, we should be now this will be our roots for this equation. Now there are possibilities that it might be real or distinct, it might be real and repeated, and there is also possibility that the roots might be imaginary. If it will be in the case when the discriminant right here gets negative and under root of negative gives us a value in the form of iota or an imaginary number. So roots might be imaginary. So there are three cases. Let's go through each one of them and try to find out the Laplace inverse for each type of a partial fraction. Now for the first case, when the roots are real and distinct, and by that I mean that when we are having a function whose denominator roots are real and distinct, if we simplify this equation, we will get these two factors, and if we equate this denominator to 0, our roots would be -1 and -2, which are real and distinct, right? They are real numbers and they are also different from each other. So for that, we can simply convert it into the partial fractions, which would be a constant divided by s plus 1 plus another constant divided by s plus 2, right? Now, how would we find these two constants? Let's move to that. So for the first case, when the roots are real and distinct, we would try to multiply the whole equation with this first denominator, and that would provide us with the equation like this. And the second step would be to take the first root of the denominator and place it of s. So s can be -1 and s can be -2. Now for this case, we would take s as -1, and once we take s as -1 in this whole equation, then it would make this term equal to 0. -1 plus 1 would be 0, and we would be left with a value of a is equal to 2, right? Now when we found one constant, what about the other constant? We would multiply this whole equation with the second denominator, and that would be providing us with the following equation. Once you multiply the whole equation with the s plus 2, which is the second denominator, then we would take s as our second root, which would be -2, right? When we equate this denominator to 0, our second root would be -2. We will take s as -2 now. This will make this whole term equal to 0 when we take s as -2, and we would be left with only b. our final value of b will be equal to negative 2. So we got both of these constants for the case when the roots are real and distinct, and our final partial fractions would be these would be our final partial fractions. Now once we have converted this function into our partial fractions, now these are the forms that we can look up for in the table 2.1, and we would see that our Laplace transform of exponent power negative 80 into unit step function is equal to 1 divided by s plus a. Right? So these resemble somehow these functions, right? And with the constant 2, so we can take the 2 common, it will not be any problem. So our final result would be, this would provide us with constant which can be taken common, so it will be the same, and then a in this case is 1, so our inverse of this function would be, and then we have a negative right here, and the inverse of this term would be again taking the 2 common, and then the a in this case is 2, right? So it will be exponent power negative 2t into unit step function, right? And this will be our final output function in terms of the time domain. For our second case where the roots are real and repeated, so if we equate this term denominator to 0, we will be having s is equal to negative 1, and then s is equal to negative 2, and the other s is also equal to negative 2. So these values are actually real, but the negative 2 is repeating itself 2 times, so we would say that the roots are real and repeated. Now for this case, when to convert them into the partial fractions, we would keep 2 constants the same way as they were in the previous case, but we would also be adding another one for the repetition. So it will be s plus 2 whole square. Now in order to find out these constants, the first one, a, we would be using the same technique by multiplying the whole function with s plus 1, and our final function would be 2 divided by s plus 2 whole square. Now in order to find a, we have to take s is equal to negative 1, which was the first root of this denominator. While when we take s is equal to negative 1, both of these terms get to 0, right? And here if we take s is equal to negative 1, then we get the result as 1 square over here, which means that our value of a will be equal to 2. So we found out our first constant. In order to find out our second and third constant, the next step would be that we have to multiply this whole equation with s plus 2 whole square, and our final equation would be, now we would be left with 1 s plus 2 right here. Now while taking the root of the equation as negative 2, which means we would replace s by negative 2, so let's do that. This term would get to 0, and this term would also get to 0. So our final term, final constant, which is c, would be equal to negative 2. So we found our second constant, which is c is equal to negative 2. For our third constant, which is b, we have to replace the value of a and c by the values that we just found. So So a was 2 and c was negative 2. Now to find b, we have to multiply this whole equation with this whole denominator. And our final equation would be, so this will be our final equation. For that we can cancel out s plus 1 over here, right here. Now our next step is to equate the coefficients. So here we are having just constant, and we also need to find out a constant value on the other side, and those must be equal, right? So let's try to find out the constant on this side. So we have constant 2 on this side, and the constant on this side would be, so in order to find b, we separated the constants on both sides, and then we equated them, so the constant must be equal, right? So our final value of b would be equal to negative 2, right? So that's how we would find out in the case when there are real roots and repeated as well. After we have converted this function into its partial fractions, then we have to look for each one of them in the table number 2.1, right? And we will try to find out its Laplace inverse. Okay, so let's do that. Now for the first one, we can see that if we look at table number 2.1, you would see that um, it resembles to our Laplace transformation of exponent power negative at into unit step function, which is 1 divided by s plus a, where in this case a is equal to 1 again. So our Laplace transform for this term would be equal to 2 exponent power negative t into unit step function, while the Laplace transform for the second term would also resemble the same frequency domain function, and its Laplace transform would be now for the third one. If you look at the table number 2.1, we would see that it resembles t into unit step function, which is obviously 1 divided by s square, and then we can shift this one by multiplying it with negative at into t into unit step function, which will make it 1 divided by s plus a whole square, right? Now it resembles exactly as this function, so our, our Laplace inverse for this one would be 2t into exponent power negative, as a is 2 in this case, so 2t into unit step function, right? So this will be our final Laplace inverse for this function, which will be then represented in the time domain, right? So this will be the procedure whenever we are having real roots and they are repeated. Now for the final case of partial fractions, when the roots are imaginary, and by imaginary we mean that when the denominator is equated to 0, we find the root which are the values of s that are not real but imaginary. Like for example, in this case, if we cannot factorize this term, if we try to find out the roots using the quadratic formula, which is is our final result, which means that the discriminant, which is b square minus 4ac, would be a negative value, right? So under root negative value is provides us with the iota or an imaginary number. Like in this case, we have value of b is equal to 2 and a is 1 and c is 5. Let's try to find out if it is negative or not. So we will be having 2 square, it should be 4 minus 20, and it will be giving us negative 16. So it is negative under the roots, so our roots would be imaginary in this case. Now let's try to find out the partial fractions for the function which is having imaginary roots. So if this is the function given, then our partial fraction would be a by s as previously, and this cannot be factorized or simplified, so it would be a second degree denominator. So we would place two constants rather than placing one constant, so it would be bs plus c. Now let's try to find out the value of constants. For the value of a, it would be mostly the same, just multiply this whole equation with the s. First root is 0, so you would take s as 0 in the first equation. That means it will make this term equal to 0, and this would also be 0, so our value of a would be, so we found our first constant, and let's try to find the other constants. Now in order to find the other two constants, we have to multiply this whole equation with this whole denominator right here, and our equation would be left with 3 is equal to this will be our final equation once we multiply this whole denominator with the whole equation. Now in order to find the constants a and b and c, we have to replace a with the value we got, where a was 3 by 5, but let's keep it same for now and try to simplify it. So 3 would be a square Now let's separate each one of separate them basis on the basis of the power of the variable they are having. So our s square is with a and b, right? And the s is with 2a and c as well, right? And then we have a constant which is 5a. Right here. Now we have to equate the coefficients of s square and coefficients of s. So we have coefficient of s square as a plus b and the coefficient of s is 2a plus c. But on the other side, we have only 3 as constant. That means the coefficient of s square is 0 and the coefficient of s is also 0 on the other side. And we only have 3 left over here. So that means that this value right here, which is the coefficient of x square on the other side, would be equal to 0, and the coefficient of s would also be equal to 0. Now let's equate the coefficient of s square and the coefficients of s on both sides. So we already know the value of a is 3 by 5. It means our b would be equal to negative 3 by 5. In this case, we know that a is 3 by 5, c is equal to 0. That means our c would be equal to negative 6 divided by 5. Right? So we found a, b, and c, where a was 3 by 5. Right? Now we have finally divided it into partial fractions with the constant 3 by 5, negative 3 by 5, and negative 6 by 5. Let's try to find find out its transformation. Now for this term it will be the same. It is the constant divided by s, so it will be the Laplace transform of a unit step function. So for this term it will be 3 by 5 into unit step function. But as you move to this step, now there is a quite complex term, and we don't have this term in our table as well. So for that we need to do some steps. We need to understand some steps. Now here you need to be very attentive in order to understand this, because if you understand this, you will be able to solve any kind of Laplace inverse with the imaginary root. So for if we look at the table, we will be having a Laplace transformation of cos omega t, which is s divided by s square plus omega square, and then we are also having Laplace of sin omega t, which is omega divided by s square plus omega square. Now if we shift them, that means we will be multiplying it with exponent power negative at, right? And here we will be shifting it to s plus a rather than s, right? And it would also get s plus a. And same will be happening with the other term if we shift it to exponent power negative at. Okay, so if we shift them, then we would get these terms as Laplace transformed. Now, if we have some constant over here, let's suppose it is a constant a, and this one is having another constant b. Okay, then those constants would be the same over here and with that one as well. Now, if we add these two, that means we will be getting something like this. So this will be our final term once we add both of them. Whenever we have a function in the frequency domain with an imaginary root denominator, then we need to convert it into this form. And once we convert it into this form, then we will be able to return it back to its original time domain form. So let's convert this one into this form. We already know the Laplace transform of this function. In order to convert this one into this one, I'm just considering this term right now over here. So I will treat negative 3 by 5 common from here to make it simpler, and then you will be left with s plus 2 divided by s square plus 2s plus 5. Okay. Now we need to factorize it, but we cannot. So for that we would be making it complete square, and let's do that, because we are having a square over here, so we want this to be square and we want this to be square. Let's do that. Now in order to make it complete square, I will be adding plus 1. This is my complete square, which is s plus 1 whole square. Right? And if here I'm getting s plus 1 whole square, so I also need an s plus 1 right here, because it is s plus a whole square, so here I need s plus a, right? So I will take it as s plus 1, right? And then it was 2 originally, so I would write here as 1, okay? And then I am having s plus 1 whole square over here, and this would be left with 4, which is 2 square, because I need omega square, so I would, rather than writing 4, I would write it as 2 square. Now I know this is omega squared, and here we are also having omega and constant b as well. So if this is omega squared, then I need to have here an omega over here, which is 2, but originally the term was 1, so to make it 1, I would put the constant as 1 over 2. Now we have almost converted this into this form. Now we know that the Laplace transform of this function would be this one, but the inverse Laplace of this function would be this term. Now we have converted this term into this form, right? So let's take the inverse Laplace transform of this function, and it resembles this one. So our inverse Laplace of this would also resemble this term in the time domain. And let's see, the Laplace inverse of this function would be equal to, as our term a is 1, so let's not mention it. Then we have shifted it by a, right? Shifted it by a, where it is 1 over here, so we will be having exponent power negative t, because a is 1, and then cos of omega t. In this case, omega is 2, as you can see it right there. And then omega 2t plus b in this case is 1 by 2 exponent power a is 1, right? So it will be negative t, and then sine of omega is again 2. So this will be our Laplace inverse of this function. I hope it is clear. This was all about inverse Laplace transformation. Thank you so much for watching. If you still have any issue, please do comment. I would be more than glad to answer. If you liked my video, please hit that thumbs up. If you haven't subscribed yet, please do subscribe. Would really appreciate the support. Wishing you the best of luck.